Biaxial crystals belong to the orthorhombic, monoclinic and triclinic crystal systems. Their lower symmetry is evident in their interference figures. 2 optic axes are present. Biaxial interference figures are used for determining optic sign using the accessory plate and the angle between the optic axes. 3 mutually perpendicular principal vibration directions are present, X, Y and Z. And here they are, and the corresponding refractive indices are alpha, beta and gamma. The birefringence is gamma minus alpha. X is always faster than Y, which is always faster than Z. Although there are 3 principal vibration directions, only 2 are activated in a typical random grain, a fast vibration direction X dash and a slow vibration direction Z dash. The optic axes intersect at an angle called 2V, or the optic axial angle. Y vibrates in all directions normal to each optic axis in the same way as O vibrates normal to the C-axis in uniaxial crystals. Thus, there's a circular section normal to each optic axis, here represented by the dot in the middle. Here are the 2 optic axes again. The optic axes lie in a plane called the optic plane. This plane contains virtually all the biaxial directions. The X and Z vibration directions also lie in this optic plane, and they bisect the angles between the optic axes. The acute bisectrix, BXA, is the vibration direction bisecting the acute angle between the optic axes. The obtuse bisectrix, BXO, is the vibration direction bisecting the obtuse angle between the optic axes. Y vibrates normal to the optic plane, here shown edge on. Optic sign depends on the vibration directions coinciding with the BXA and BXO. Biaxial positive minerals have Z equal to the BXA and X equal to the BXO. Optically negative is the other way round. Here's the biaxial indicatrix, the 3-dimensional configuration of the 3 vibration directions and the 2 optic axes and their circular sections. Z is vertical, X horizontal and Y normal to the plane of the diagram. The indicatrix is being rotated about Z. Here we're looking at the optic plane edge on, and here we're looking normal to the optic plane coming round to the position right now. And here we're looking normal to the optic plane again. Indicatrix is now rotating about X, so we look down the BXA, the vibration direction bisecting the acute angle between the optic axes. We're zooming in down the BXA. And rotating and tilting to see one optic axis. And tilting back so we look down the optic axis. And now rotating back so we look down the BXA between the 2 optic axes. And that's straight down the BXA right now. And then continuing to rotate and look down the other optic axis, there. And then continuing to tilt the indicatrix a bit to show its typical shape. This animation sequence is repeated, speeded up about 6 times. The optical behaviour of biaxial minerals depends on the direction of incident light relative to the indicatrix. I'll demonstrate the different situations. Firstly, light travelling along an optic axis. Only the Y vibration direction is activated. Birefringence is 0 and the grain is pseudo-isotropic. This grain gives an optic axis figure. Secondly, light travelling along Y results in X and Z vibration directions and the maximum birefringence. This is the random orientation, which applies to most grains in the slide. Birefringence is less than the maximum, and the vibration directions are X dash fast and Z dash slow. A special case involves light travelling along the BXA. This is split up into the Y and BXO vibration directions. Birefringence is less than the maximum. Light travelling along the BXO is another special case. The Y and BXA vibration directions result. I've now shown you the directions of incident light relative to our work. We start with BXA figures as they demonstrate the biaxial directions and help us understand the more useful optic axis figures. The acute bisectrix is vertical in a BXA figure. We're looking down the acute angle between the optic axes. Lower symmetry and breakup of the isogaia cross are obvious differences from uniaxial optic axis figures. There are 2 main configurations, a cross when the optic plane is east-west or north-south, and curved isogaias when the optic plane is diagonal. The optic axes always lie along an isogaia, and isochromes are roughly concentric about them. We need to recognise the various optic directions in BXA interference figures. In this position, the BXA is vertical and is represented by the cross in the centre. First, find the optic axes, then draw in the trace of the vertical optic plane through the optic axes. Y vibrates normal to the optic plane everywhere along the trace of the optic plane. So it's handy to sketch those features on paper. Rotating the stage 45 degrees makes the cross break up into curved isogaias which move apart to their maximum separation. The directions are as before, but are rotated 45 degrees. The BXO vibrates within the optic plane. The greater the birefringence and the grain thickness, the more isochromes in the figure. This is a very high retardation BXA figure with about 10 orders of colours. This one has about 3 orders of interference colour. And this figure has low retardation, first order white. Most interference figures from grains in thin sections show these interference colours. The 2V angle affects the maximum separation of the isogaias when the stage is rotated 45 degrees from the cross position. Here 2V is 0 and there's no separation. Here 2V is 45 degrees and the optic axes are near the edge of the field of view. Here 2V is about 60 and the optic axes are outside the field of view. Here's a series of BXA figures showing the maximum isogyre separation for decreasing 2V. 2V 60 degrees, 2V 45 degrees, 2V 20 degrees, 2V 5 degrees, and notice the slight separation in the middle, 2V 0. Optic sign is determined with the isogyres at their maximum separation in the 45-degree position. For the first few attempts, sketch the figure on paper and label the following optical directions: the optic axes, blue dots, the trace of the optic plane passing through the optic axes, the vibration directions in the middle of the field, Y vibrating normal to the optic plane, and the BXO parallel to the optic plane. Remember that the BXA is vertical. The aim is to determine if the BXO is X, which is optically positive, or Z. So to plate in, we get a rise. And the slow vibration direction in the plate is northeast-southwest. The middle of the field is equivalent to the northeast and southwest quadrants in a uniaxial figure. The northwest and southeast quadrants lie outside the isogyres. There's a rise in the middle, so Y is slow. Y can only be slow compared with X, not Z. Therefore the BXO is X, and the BXA is Z, and the mineral is biaxial positive. Always rotate the stage 90 degrees to check the opposite effect of the plate. The fall here confirms the rise in the first position. You don't have to work out the optic sign from first principles every time. Just find the northeast quadrant and apply the rule. A rise, R, in the northeast means optically positive. A fall, F, means negative. Note how the uniaxial and biaxial quadrants correspond. Here's one for you to try. Watch the first order red isochrome. Plate in, plate out. Rotate 90 to see the opposite effect, plate in, and rotate back to the first position. There's a rise in the middle, that is the northeast-southwest quadrants rise, therefore biaxial positive. There's a rise in the middle, that is the northeast-southwest quadrants rise, therefore biaxial positive. Here's another one for you to try. Plate in, plate out, rotate to see the opposite effect, plate in, plate out, plate in again, and rotate back to the first position, and there's a fall in the first position, so the mineral is optically negative. Optic axis figures are the main interference figures we use to determine optic sign and 2V. In optic axis figures, light travels vertically upwards along an optic axis. Here's an example of an optic axis figure. Can you see that it represents part of a BXA figure? Here's a view of the biaxial indicatrix again to show how an optic axis figure is related to a BXA figure. There's the view for an optic axis figure, and there's the view for the BXA figure. For low 2V, there's not a lot of difference between them. Here's a BXA figure produced by a glass bead held over a grain under low power. Find the optic axes and remember the trace of the optic plane passes through them. So I'm just rotating the stage, and it's a normal BXA figure. Here I'm twisting the mineral grain, so one optic axis and then the other is vertical. Now I'm rotating the stage 45 degrees, and I'll repeat that rotation of the mineral grain about the Y direction from one optic axis to the other. So this shows how an optic axis figure is a special kind of off-centred BXA figure for 2Vs of less than about 40 degrees. The appearance and behaviour of optic axis figures depends on 2V. The first example is for a low 2V of about 5 degrees. The blue spots mark the optic axes. Note the slight separation of the isogyres and their stronger curvature near the optic axes. This is the optic axis figure for 2V around 45 degrees. The other isogyre and optic axis is outside the field of view. The isogyre curves more gently than for low 2V, and the BXA is on the convex side of the isogyre. Finally, here's the optic axis figure for 2V around 85 degrees. The isogyre rotates like a two-bladed propeller and is only slightly curved in some positions. Sign determination is demonstrated for moderate 2V. Rotate the stage to a 45-degree position in which you can recognise the quadrants. The BXA is always on the convex side of the isogyre. For the first few attempts, it helps to sketch these directions on paper. Locate the optic axis. Mark in the trace of the vertical optic plane. Show Y vibrating normal to the optic plane. A direction close to the BXO vibrates within the optic plane on the convex side of the isogyre. The other optic axis and its isogyre is outside the field to the northwest. With the plate in, for the northeast-southwest quadrant there's a rise, therefore Y is slow, so the BXO is fast and must be X, therefore biaxial positive. Or from the quadrant rule, rise in the northeast means positive. We can rotate the grain 90 degrees and identify the quadrants and test again. Sign determination is now demonstrated for a high 2V optic axis figure. The isogyre has much less curvature. Here the northeast-southwest quadrants lie across the upper left, and with the plate in, we get a fall in those quadrants, so it must be biaxial negative. 2V can be estimated from the curvature of the isogyre. Here 2V is less than about 20 degrees, and really it's a BXA figure. All optic axis figure isogyres are straight when east-west or north-south, regardless of 2V. To measure 2V, rotate the stage 45 degrees from this position, and this is the curvature for a 2V of about 20 degrees. Repeating this for 2V around 45 degrees, start with the isogyre straight, rotate 45 degrees, and note the curvature. Finally, for 2V around 85 degrees, rotate the stage 45 degrees from when it was straight, and note the curvature, it's still almost straight. If the optic axis is tilted too much from the vertical, the isogyre moves outside the field during stage rotation. 2V cannot be determined, and it may be difficult to distinguish biaxial from uniaxial. The isogyre must remain in the field for the optic axis figure to be useful. Normally, we don't get interference figures from maximum interference colour grains. Biaxial flash figures closely resemble uniaxial flash figures. Most of these properties are determined in the same way as for uniaxial minerals. Some properties like pleochroism require different procedures. Procedures for extinction and optical orientation are generally more complex than for uniaxial minerals. Procedures differing from those used for uniaxial minerals will now be explained. Biaxial minerals can be colourless and non-pleochroic, coloured and non-pleochroic, or coloured and pleochroic. Here is a coloured non-pleochroic mineral. Here's a pleochroic mineral. The three grains show different colours because they are orientated differently. These are the three pleochroic colours to be equated to the vibration directions X, Y and Z. Not every vibration direction produces colour in minerals. One or two can be colourless. With stage rotation, one grain changes from pink to green, one from pink to yellow, and one from yellow to green. The absorption scheme expresses the relative absorption of X, Y and Z. Here, the relative absorptions are all roughly the same. Here's the pleochroic behaviour of individual grains of the same mineral. The colour here changes from pale green to pale yellow. Here's a grain changing from pale pink to pale green. Remember, when the grain is pink, the pink vibration direction is east-west. And when the grain is green, the green vibration direction is east-west. Finally, here's a grain changing from pink to yellow. To determine the pleochroic formula, we need two grains, the maximum interference colour grain and a dark first order grey grain. First, scan the slide to find the maximum interference colour grain. The interference colours here go up to first order yellow, so we need to keep looking. Here's the maximum interference colour grain, first order red. Of all the grain orientations, this is the one most likely to show pleochroism. Rotating in plain light shows that the two colours are green and pink. We know one is X and one is Z, but which is which? To find out, rotate the grain until it is at the limiting position for one colour. And here the green vibration direction is east-west, parallel to the polarizer. Rotate the green vibration direction about 45 degrees anti-clockwise. And there's the ray, the green ray, northeast-southwest. Cross the polars and insert the accessory plate with its slow vibration direction northeast-southwest as shown. The interference colours appear to rise to second order red. Rotate 90 degrees anti-clockwise. The interference colours fall to black. Plate out, plate in. so that is a fall. Rotate back to the first position, plate out, and so the interference colours rise when the green vibration direction is northeast southwest. So green is slow and must be Z. So there's the green ray rotated east-west. And the other vibration direction is X and is pink. So X equals pink and Z equals green. And the relative absorption is X approximately equal to Z. The Y colour is best obtained by setting the Y vibration direction east-west using an optic axis figure. First find a dark first-order grey grain to get an interference figure. The optic axis should remain in the field of view for the figure to be useful. Rotate the stage to check this. Rotate the stage until a trace of the optic plane is north-south, and then the Y vibration direction is east-west as shown. Returning to the grain, Y is vibrating east-west, parallel to the polarizer. Without rotating the stage, check the colour of Y in plain polarized light. And Y is equal to yellow, and the Y ray absorption is similar to that for X and Z. If we rotate the stage, the colour does not stay the Y colour because the optic axis was not perfectly vertical. This shows the value of using the figure to locate the Y direction precisely. The results are recorded as shown here in this shorthand format. All these related properties can be determined only if parallel-sided crystal form is present. Use the maximum interference colour grain for these properties, as this is a fixed orientation with X and Z parallel to the microscope stage. Biaxial minerals fall into two main groups, orthorhombic with parallel extinction and monoclinic and triclinic with inclined extinction. Procedures for minerals with parallel extinction are demonstrated first. Rotate the maximum interference colour grain to confirm parallel extinction. First, rotate to extinction. And there's the grain north-south. At extinction, the vibration directions are north-south and east-west, but we don't know which is X and which is Z. The procedure is the same as for uniaxial prisms, except that here the maximum interference colour grain contains X and Z, not O and E. Rotate the prism about 45 degrees clockwise so the C-axis is northeast-southwest, parallel to the slow direction in the plate. Add the plate. The slow direction in the plate is northeast-southwest as shown. The interference colours seem to rise to second-order red or third-order blue. To check this, rotate 90 degrees to see the opposite effect, and the interference colours have fallen to black. Rotating back to the first position with the plate still in, this was a rise. Therefore, the northeast-southwest vibration direction must be slow and is Z. So when the C-axis of the prism is rotated north-south, the vibration directions are north-south and east-west. Z is north-south, and X is east-west. We now sketch this configuration. And here's the orientation sketch showing the crystallographic features, the prism and C-axis, and the optical directions, the X and Z vibration directions. I'll repeat this procedure for another prismatic mineral. Rotate the maximum interference colour grain to confirm parallel extinction. Set the long axis northeast-southwest parallel to the slow in the plate. With the plate in, the prism stays first order white to yellow. To check, rotate 90 degrees to see the opposite effect. And here there's a rise to second order green. So returning to the first position, this must have been a fall. Therefore the fast vibration direction, that is, X, is parallel to the long axis of the prism. So X is parallel to the long axis and Z is normal to the long axis, and we can now sketch this orientation. And here's the orientation sketch showing the crystallographic and optical directions. Monoclinic and triclinic minerals generally show inclined extinction. I'll demonstrate these procedures for inclined extinction. As before, select the maximum interference colour grain. X and Z will be parallel to the plane of the stage. Note the inclined extinction. We have to locate the vibration directions and measure the extinction angle. Remember, the vibration directions are north-south and east-west at the extinction positions. Rotate the stage to make the C-axis north-south. And note the stage reading in degrees for this position. Next, rotate the grain to extinction and try to get that position exactly. Note the stage reading. Subtract the two stage readings and the angle's about 25 degrees. So we've measured an extinction angle. Sketch the grain in the extinction position. The vibration directions are north-south and east-west as shown, and the C-axis is parallel to the prism. So the measured extinction angle is the angle between the north-south vibration direction and the C-axis. We now have to determine which vibration direction is X and which is Z. So we rotate the north-south vibration direction about 45 degrees clockwise, parallel to the slow in the plate. Add the plate with its slow direction as shown, and the interference colours seem to rise to second order red. To check, rotate 90 degrees to see the opposite effect, which is a fall to black, so this confirms the rise in the first position. Therefore, Z vibrates northeast-southwest and X vibrates northwest-southeast. Now sketch the prism in this position, showing the crystallographic and optical features. The crystallographic features include the prism outline, the C-axis and the cleavage, and the optical features include the X and Z vibration directions and Z angle C. Y is normal to the diagram. And here's the two-dimensional orientation sketch summarising these relationships. These help us understand the appearance of crystals and their optical behaviour. Here's a typical orientation diagram for a clinoamphibole. I'll point out its components. Crystal faces, the 110 prism, 4 faces, the main form, the 010 pinacoid, 2 faces, and the 011 form at the ends. Crystal axes, A front and back, B left to right, and C vertical. Prismatic cleavage is shown as parallel traces on vertical faces. Optical directions. X and Z define the optic plane, OAP, parallel to 010. Arcs define the ends of the optic axes, and Y is normal to the optic plane. Here's a simpler version of that crystal showing just the cleavage traces in red. The prism is rotating around its C-axis. Now it's rotating around the B-axis to show the end on view, the typical amphibole cleavage pattern. Here's the same crystal showing the X, Y and Z vibration directions. It's a simplified version of the detailed 3D diagram for the clinoamphibole. And now this crystal's being rotated around the B axis for the end on view. Here's a simplified model of the clinoamphibole rotating around the C-axis, which is white. X is red, Y is yellow, and Z is green. Y coincides with the B axis. For simplicity, X is made to coincide with the A axis. The 4 110 prism faces are terminated with the 001 basal pinacoid. Note how X, Z and C all line up for certain positions, so that the crystal appears orthorhombic, not monoclinic. That's the front view, it looks orthorhombic. And that's the side view, it looks monoclinic. Here's the view parallel to 100. Z is apparently parallel to C, so that this grain will show parallel extinction. Here's a view roughly parallel to 110. Z appears to make a small angle with C, so the grain will show a small extinction angle. And here's a view parallel to 010. Z makes the maximum true angle with C. The grain will show the maximum extinction angle, Z angle C, and the maximum interference colours. This sequence of two-dimensional sections shows the change in the apparent relation between the vibration directions and the crystal directions as the crystal is rotated from the 100 section to the 010 section. Note how the extinction angle between Z or Z dash and C increases. I'll now demonstrate the effect of grain orientation on crystallographic appearance and optical properties using tremolite in vinssection. Note how the crystal outline, cleavage, interference colour and extinction angle vary from grain to grain. Here's a grain cut parallel to 100. Cleavage traces are not visible as the cleavage planes are inclined too gently to the plane of the section. This grain shows parallel extinction, so it appears orthorhombic. This grain corresponds to the first of these two-dimensional orientation diagrams. This prism, cut parallel to 110, shows a higher interference colour and one set of sharp cleavage traces. Extinction is inclined with an extinction angle of about 10 degrees. And there's the extinction position. This grain corresponds to the middle diagram. This prism is cut parallel to 010. It shows the maximum interference colour and weak cleavage traces. Extinction is inclined. The extinction angle is about 20 degrees, the maximum angle. And this grain corresponds to the last orientation sketch. In summary, we've seen how the extinction angle, the interference colours and the appearance of cleavage have changed with grain orientation. Other orientations are possible. This 001 section shows the view looking down the C-axis. The grain shows symmetrical extinction. Two sets of cleavage traces are visible, parallel to the 110 prism faces. Note the 60-degree angle between these cleavage traces. This cross-section is characteristic of amphiboles. This dark first-order grey grain represents another special orientation, looking down an optic axis. The optic axis isn't exactly vertical, as the grain shows extinction positions. This is the type of grain we need to find to get a useful interference figure. Well, that covers the special orientations. Most grains in the fin section are like this and represent randomly oriented sections through the prism. Such grains are cut at variable angles to the C-axis and to the X, Y and Z vibration directions. These grains have an X' vibration direction between X and Y in its properties, and a Z' vibration direction between Y and Z. You should now be able to understand how grains of the same mineral can vary so widely in the same section. This is good practice for understanding the relationships between two-dimensional sections and three-dimensional reality in general.